Okay, so welcome to the Oxford Discrete Maths and Probability Seminar. As usual, we'll keep everyone muted, but please do ask questions in the chat, and Christina and I will curate them and interrupt the speaker if something needs asking immediately. Otherwise, questions can wait till the end. So this week, it's as our first talk today, we have it's a great pleasure to have Yuval Peled. And he's going to talk on minimum weight, disk triangulations, and fittings. Thanks.
Yeah, thank you, Alex, and thanks for the invitation. The title of this talk is a joint work with Itai Benjamini and Eyal Lubetzky. But I'm going to start by talking on a older work with Zur Luria on random simplicial complexes. It will, I think, I hope help put things in the right perspective. So let's start. So, first, a very brief introduction to simplicial complexes. Well, a simplicial complex can be viewed in two ways. One is as an abstract object, which is just a family of subsets that is closed under taking subsets, and the other way is to associate to each of the subsets here a geometric simplex and glue these simplices according to the labels, hence creating a topological space. So, so the sets of size 1 will correspond to vertices, so every 5, and the sets of size 2 will correspond to edges, size 3 to two-dimensional simplices, and so on. You can of course say that this framework contains the notion of graphs, which are one-dimensional complexes. In this talk, we will only focus on simplicial complexes of dimension 2 and less. So this is a good picture to have in mind. This concept is usually used to have a finite discrete representation of topological spaces, which makes things much easier to work with. And what we want to do here is like in light of the importance of random graphs, Eyal and Meshulam introduced and started to study random simplicial complexes. So this shouldn't be here. Let me erase this. They introduced a model which is a two-dimensional extension of G and P. So it's called Y2 and 2 and P2 is for the dimension of the complex, and is for the number of vertices, or for the set of vertices. They say, let's add all the edges to edges. This is what is called a complete skeleton, and then put all the randomness in the two-dimensional level, and choose each of the and choose 3 two-dimensional faces independently with probability P. So like if n is equal to 4, just to have something concrete in mind. So you'd have the 4 vertices here, 1, 2, 3, and 4. You would put all the 6 edges between them, and then each of the two-dimensional faces you will add with a probability P. So like for instance, you can add this face and this one, and let's say that this one and the face one before you did not. So you can have a random model of two-dimensional complexes, which is of course, if you think about it from a combinatorial perspective, it is just a binomial tree, uniform random hypergraph. But the issue is, or I guess the point here is that if you think of this object as a simplicial complex, it leads you to a different set of questions that are more related to the topology of this object. So, for instance, the first theorem that Eyal and Meshulam proved on this is an analog to Erdősen Rainy result on connectivity of random graphs, and it deals with the vanishing of the first homology of the complex. So let me give you a one-line definition of this concept right here, which we can and they called as homological connectivity. So if you have a complex, let's say a two-dimensional complex, and you want to somehow capture the notion that it has no holes in it. So you would want for every cycle to exclude the possibility that this cycle is circling a hole in the complex. So you can say I wanted every cycle, which is now just seen as a so we think of a cycle as the characteristic vector of a cycle on the set of edges. So you would have here like this pink cycle right here would be a vector with ones here and zeros everywhere else. And you say, well, can I write this cycle as a linear combination, or over f2 as a sum mod 2 of boundaries of the two faces of the complex? If I can, then that means in this sense that this cycle is not a didn't find a hole in the complex. And if I can do that for every cycle, then this means that the complex is homologically connected. So for instance, in the two examples I wrote down here, so here, of course, you can do that by taking the sum of both faces here, and hence this edge will cancel out. Well, here, of course, you can, because this edge is exposed or uncovered, so no boundary can be used to describe a cycle that uses this edge. And indeed, like this is a good example to keep in mind when reading the theorem of Lineal and Meshulam, who said that the random complex is homologically connected exactly when or at the same probability, where, so this concept right here is this 2 log n over n is the probability of having an exposed edge. So this is, or let's call it an uncovered or isolated edge, which means an edge that is not covered by any two-phase. So this part is of the argument is just a straightforward coupon collector argument, while the other side takes all the work. And again, this is a situation that is very similar to the connectivity threshold in G and P. And I've written here, but I do not want to get into that this was extended in pretty much every way you can think of. And by now I can say that this a phenomenon of homological connectivity we know very, very well, and it is completely understood. A notion of connectivity that is much less understood in this random setting is the notion of simple connectivity. So this was first studied by Babson, Hoffman, and Kale. So a complex is called simply connected if every cycle is null homotopic, which means that one can map a disk, a two-dimensional disk, into the complex, such that the boundary is mapped to the cycle, and like this gives a way to contract this cycle into a point in the simplicial world. One can give a more combinatorial criteria by saying that for every cycle there is a triangulation of the disk, like we see here, such that the vertices of the triangulation are labeled by the vertices of the complex, in this case 1 up to n. The boundary is the cycle that we want to contract, and all the faces of the triangulation, when seen as labeled faces, for instance, this 4, 5, 11 here, are taken from the complex. And Babson, Hoffman, and Kale showed that if P is less than n to the minus f minus epsilon for any epsilon, the random complex is not simply connected with high probability. So, and in fact, they show that if you pick a fixed cycle of length 3, let's say 1 to 3, like here, the with high probability, you will not be able to find such a triangulation. And to improve this bound is open, very interesting and very hard. So why is it so hard? Mostly because so in this definition, we're not required to use each vertex only one time. So we can, and I wrote here two interesting examples of triangulations where you can actually must with with these sets of faces to use vertices, and here also faces like this. The face 4, 5, 7 is used more than once. So so to get control like in the sense of I'm saying to get a sufficient combinatorial understanding of this set of possible triangulations to improve this bound is currently out of reach. Okay, let me take a water break. Okay. What has been done is to so we said that improving this bound is hard. One can ask, what would you aspire to improve it to? So what is the best theorem of the form if p is larger than some function of n, then the random complex is simply connected with high probability, and this was studied by several people. So first, Bobson, Hoffman, and Peled in their lower bound paper showed that -1/2 is the right exponent of n, and then this was improved a couple of times, and the most recent result is a joint work with Zur Luria, where we show that if P is 1 plus epsilon over the root of gamma n, where gamma is this constant 4 to the 4 over 3 to the 3, which is taken from Tutt's famous formula for the enumeration of planar triangulations. So this is the I guess the growth rate of the number of triangulations as a function of the number of vertices in the triangulation. So so for such P with high probability, every cycle of length 3 can be is null homotopic, and more over you can find a null homotopy that uses every vertex at most one time. So this is what you call a proper triangulation, where the labels of the vertices are distinct, and we showed that such a triangulation can be found for every cycle of length 3, which is easily can be shown to imply that the complex is simply connected. We conjecture that this is sharp. So namely, it is not hard to see that this thing is, I guess, in some sense, let me be careful here, but like that this gamma to the half is the sharp threshold for having proper triangulation, and we conjecture that this is also the sharp threshold for simple connectivity. So namely that that the proper triangulations are the ones most likely to appear first in a random complex. So when I think that it's a good time to recap what we said so far. So this is the I think a good recap picture. So we mentioned three notions of connectivity. One is the a notion of homological connectivity, whose threshold is at 2 log n over n. We mentioned the notion of simple connectivity, where every cycle has a null homotopy, and we saw a lower bound of n to the minus f minus epsilon, and then we saw a stronger notion that we mentioned of null homotopy by a proper triangulation that has a sharp threshold that gamma n to the minus 1/2, and we have this conjecture of whether or not they are equal. With Itai and Eyal, we wanted to look at these three notions of connectivity in a different probabilistic in a different probabilistic model. This is an extension of the model of first passage percolation on the complete graph, and this is what I mean. So instead of taking a random subset of the faces, we take all the two dimensional faces and assign each face with an independent, let's say, exponential one random weight, and then instead of asking, as we did here, if a certain notion of feeling appears in the complex, we fix a cycle. Let's say the cycle 1, 2, 3, and we ask what is the total minimum weight of a triangulation whose boundary is this cycle, and just like we did in the model of random complexes, we can also ask here about three different about the three different notions. We can ask what is the minimum weight of a minimum total weight of a proper triangulation of the cycle. We can ask what is the on the other hand, what is the minimum total weight of a way to write the cycle 1, 2, 3 as a mod 2 sum of the two dimensional simplices, and we can also ask what is the minimum weight of a null homotopy of the cycle. So these are three questions that we can ask, and I think that by a first side, you can derive some bounds on these random random variables from the results on the random complex. So for and this is done by the fact that one can think of Y2 and P, I guess, roughly, as the all the faces of weight less than P, right? Of weight less than p. So in particular, we can use the proper triangulation found here to get a bound on the n, or the fact that any null homotopy has to use at least one face of weight at least n to the minus s minus epsilon to find this lower bound. Very good. And we were able to get pretty accurate results on these three random variables. So the first theorem that we have is that minimum weight proper triangulation is of order gamma n to the minus half times so we're able to find the main term and the second order term, which is of orders log and log n, and to show that the next order is tight, and what was a real surprise to us is that unlike the a huge gap between homological and null homotopies in random complexes in this model of minimum weight, these three notions inside, which is the content of our second theorem. Okay, so I have some time. Do I go until 9:50 or 10? Oh, okay, that's good. Okay, great. So I just wanted to mention some ideas of the proof, which I think are interesting. So let's do this one at a time. So first of all, to find the right, I guess, term for dn, we look at a random variable that counts the number of proper triangulations under a certain total weight, and using the result of that that counts the number of total of unlabeled triangulation with a given number of vertices, you can compute this expectation and find that like this is the right regime to look at. The second moment is much more challenging. So one thing that you actually learn when looking at the first moment is that the right set of triangulations that you need to look at are the ones with roughly a log n over 4 internal vertices. So the natural thing to do would be to apply a second moment method on the number of such triangulations with total weight under a certain threshold, but it turns out that this fails, and basically what you need to do to fix it is to throw out a subset of all triangulations, and it turns out that a constant fraction of all triangulations have the following structure. So you start with a small triangulation on R, which is order 1 number of vertices. Then you pick one of the faces here. Let's say I know this one, and then you do a then you add k minus r internal vertices here. So you you triangulate this a yellow face with k minus r internal vertices. So these form a constant fraction, which is not one, of all triangulations, and these make the second moment to blow up. And if you remove them, you're good, but the second moment computation itself is like shows like an interesting connection between like the topology of certain planar sets and their contribution to the second moment. But like that's what you basically need to do. For the third point, or like the second item, so you want to show that that the, so perhaps I was a little, so like you want to show that the minimum weight homological filling is equal with hyperability to the minimum weight, let's say, proper triangulation. So, well, one can first ask, give me an example of a so I guess it's, so here's an example of a homological filling, which is by homological filling, I mean just a way to take a sum mod 2 of the faces that reaches a certain cycle. So example of a homological filling that is not a triangulated disk, a triangulation of a disk. So this is what we see here is the example, right? I mean, if you take any surface with a boundary, of course you can still sum all the faces in the surface to get this boundary, which is this pink cycle right here, but it is not a disk, and it turns out that basically every homological filling contained such a surface, and then what you need to do is to extend this first moment right here to a sum not on triangulations of the disk, but on triangulations of all the surfaces, and you get to something very nice, which is like it turns out that the contribution of a surface to the sum is related to its genus, and hence the sphere or the disk is like the optimal surface, and this like sort of sums appear floating random matrix theory, and so that was like a nice part of the proof, and eventually this is how you show that the best surface is the sphere, hence this is true. Okay, so I think I'm gonna stop here, and thank you for your patience and listen.
Great, thank you very much, Yuval, for a fascinating talk. So if anyone would like to ask questions, please do signal in the chat. We'll give people the ability to unmute as well. Maybe, Sona, I could ask a question, which was, so going back to the first half of the talk,
yes.
If I have it correctly, that as the kind of edge probability, I mean the triple probability, goes up above 1/√n, then the fundamental group becomes trivial. Is that the right?
That is so. What we know right now is the following thing, like in this language. So we know that if p is less than n to the -1/2 minus epsilon, then pi1, the fundamental group, is hyperbolic and non-trivial. And basically, we know that if p is larger than this root gamma n, then pi1 is trivial. Yes, and we don't know what occurs, for instance, if p is epsilon over root n.
Right. Okay, so I wonder whether there was anything else interesting to say about what happens to the sort of the evolution of the fundamental group as you go from p equals 0 to p is around 1/10.
So this has been studied, and people talked about, for instance, the evolution of the homological dimension of the group, or property T, like, so this has been studied. Micha Farber has lots of works on that. Yeah.
Okay, thank you. I think Christina, you had a question.
Yes. So if you take your theorem about the minimum weight disk triangulation, there was a you have this sequence of tight random variables.
Yes.
Does it make sense to ask if that converges in distribution? Is that is that something that might be true?
So I think it will be true. I'm not sure what is the limit, but I can tell you this, which is so in our paper, this was actually theorem number 3, and 2 was that if you throw out this set of triangulations, and like only like look at the set that you can do a second moment on, so let's call it the tilde. And so you have the same expression where this is some shifted Gumbel. So and the I think that the issue here is that, you know, for each of these small triangulations would like give a different distribution. Like you'd have to match between them. So it seems like a hard question, but possible. Yeah.
Okay, I think Ron had a question as well.
Yeah. So did you think about doing this kind of model on actually Z3, let's say, and doing first passage calculation where each phase gets an exponential 1, let's say, and you ask what is the minimal surface you need in order
I think that's, yes. So like that's one of the like things that we okay, I would say like this. This is definitely a natural question to ask. For instance, you can ask whether there is a Benjamini-Kalai Ram theorem where like the variance. So like just so you take like a I don't know a big n by n by n by n on a height 0, and you can ask what is the variance of the minimum weight of this. I think it's a great question. I don't know like what is the answer, or if the methods of BKS can work, but that's a very nice question, I think. Yeah.
Thanks.
Okay, I think maybe this is a good point to pause for everyone to have a tea break or coffee break. But first, so everyone has the power to unmute. So let me invite everyone to unmute and give Yuval a big round of applause.